Good evening, ladies and gentlemen, friends and colleagues. The Institute for Mathematical Sciences, or in short IMS, is a university-level research institute at NUS. Its mission is to promote interest and research in the mathematical sciences and their applications. It organizes programs with themes in areas at the forefront of current research and brings together foreign and local mathematicians and scientists for interaction, cross-fertilization of ideas, and collaboration in research. It also organizes public lectures to help instill and foster mathematical awareness and interest, and school lectures and math camps to stimulate students in the study of mathematics and inspire them to pursue a career related to the mathematical sciences. This evening's public lecture is organized by the Institute in conjunction with the NUS Department of Mathematics and the Singapore Mathematical Society. We are pleased to have Professor Jennifer Chayes of Microsoft Research as the speaker. Professor Chayes received a BA in Biology and Physics at Wesleyan University in 1979 and a PhD in Mathematical Physics at Princeton in 1983. She did a postdoctoral work in mathematics and in the mathematics and physics departments at Harvard and Cornell, and was for many years a professor of mathematics at UCLA. She's an expert in an emerging field at the interface of mathematics, physics, and theoretical computer science. Her current research focuses on phase transitions in combinatorics and computer science, structural and dynamical properties of self-engineered networks, and algorithmic game theory. She is co-founder and co-manager of the Microsoft Theory Group, as well as research area manager for mathematics and theoretical computer science at Microsoft Research. She also heads the new algorithms, computers, computation, and e-commerce subgroup of the Microsoft Theory Group, and is an affiliate professor of mathematics and physics at the University of Washington, Seattle, right? She serves on numerous institute boards, advisory committees, and editorial boards, including the Board of Trustees of the Mathematical Sciences Research Institute, after which the IMS is modeled, the Scientific Board of the Fields Institute, the advisory boards of the Center for Discrete Mathematics and Computer Science, and of the Miller Institute for Basic Research in Science, the Communications Advisory Committee of the National Academies, the U.S. National Committee for Mathematics, the Association for Computing Machinery Advisory Committee on Women in Computing, the Leadership Advisory Council of the Anita Borg Institute, and the International Union of Pure and Applied Physics Commission on Statistical Physics. She is also a past chair of the mathematics section of the American Association for the Advancement of Science and a past vice president of the American Mathematical Society. She has twice been a member of the Institute for Advanced Study at Princeton and has been an invited speaker at the International Congress of Mathematicians. She's a fellow of the American Association for the Advancement of Science and a national associate of the National Academies. I think the list goes on, and I wouldn't want to take too much of her time. I first met Professor Chayes in 1985 when I was on sabbatical leave at the Institute for Mathematics and its Applications at Minneapolis. That was also 2 years after she obtained a PhD. She left a very deep impression on me as an extraordinary young mathematician who had an impressive knowledge of her field. Although I did not meet her again until 1999, when she came to Singapore as a distinguished visitor of the Singapore Mathematical Society, I had often heard about her achievements. I'm delighted that she's back in Singapore, this time to participate in the IMS program on random graphs and large-scale real-world networks. It is now my great pleasure to invite Professor Chayes to deliver her lecture on Epidemics in Technological and Social Networks, the Downside of 6 Degrees of Separation. Jennifer.
how to turn it. This is on now? Okay, thank you so much, Louis, for that very nice, very, very nice introduction. I think I should serve on fewer committees so that I have more time to give my talk. And it's very nice to be back. I can't believe it's already been 7 years. Last time I was here, people didn't have interesting ringtones. Sorry. Right, technology. Okay, so I am going to talk about epidemics in technological and social networks. And as many of you probably know, there is a phenomenon called 6 degrees of separation, in which it seems that most people in the world know someone who knows someone who knows someone who blah, 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 six levels to anyone else in the world. And that's good in a lot of senses, but if you are talking about epidemics, it's not so good. Okay? So, and roughly 2/3 of the lecture, I'm going to go over other people's work, and then in the last third, I'll focus on some work that a few of us have done. Okay, so the first third, roughly third, I will talk about the internet, the World Wide Web, and other power law networks. There are some real experts. This is not for them. This is for people who don't know much about this. Then I will talk about models for the spread of viruses and worms. Okay, so here we're talking about power law networks. Here we're talking about the spread of viruses. And then we put them together and we talk about the spread of viruses on power law networks. Okay, so for the first part of the talk, I will first tell you how to view the internet and the World Wide Web as graphs. And I will then tell you some properties that people have seen when they've looked at the internet and the World Wide Web. We'll see that some of those properties actually look like properties that you find in social networks. And then I'll talk about models of the internet, the World Wide Web, and social power law networks. And as I said, there are some real experts on that in the audience here. Okay, so the internet and the World Wide Web as graphs. So on the poster, there was a little picture of this. This is a snapshot of the actual internet. Okay, it's colored very nicely, and I didn't do that. I just grabbed it off the web. And here is a small piece of the World Wide Web. The World Wide Web is, of course, much larger than this. It has somewhere from 5 billion to 8 billion web pages. Okay, so if I want to view this as a graph has a set of vertices and a set of edges. And so the internet, most people talk about the AS internet. And so the vertices are these systems like AOL and MSN and Yahoo. And the edges are the connections among those autonomous systems. For the web, the vertices are web pages, and the edges are hyperlinks. So I can, from my web page, have a link to Belo's web page, for example. So that would be a hyperlink from my web page to Belo's web page. And sometimes we view the World Wide Web as an undirected graph by just not looking at which direction the hyperlinks are going in. Okay, so the first property that people observed, or the first one that I'll mention, is that these power law networks seem to have very small diameters. So I can look at the shortest path from some point X to some point Y. And what I want to do is I want to look at the average distance from one point to another, but I only want to look at points that I can get to from each other. Otherwise, the average would just be infinite. Okay? And this has been measured in a lot of cases. So for the AS internet, there's only about 3 steps. If I view the World Wide Web as an undirected graph, then we see about 6 degrees of separation. And if I view it as a directed graph, then it's about 16, because let's say I have a link to Bela's webpage, but he doesn't have a link to my webpage, then I would have to take a longer path. I couldn't walk backwards over that hyperlink. Okay, and these are some of the people who did those measurements. Okay, the second property is called clustering. So I look at one vertex and I look at all of its neighbors, all of its nearest neighbors, and the clustering coefficient tells me roughly how dense this neighborhood is. So it tells me the number of edges in the neighborhood of a point over the maximum possible number of edges in the neighborhood of that point. So here it's, what is it? It's like 6, and there are like 15 possible edges. And for the World Wide Web, it turns out that some measurements show that the clustering coefficient is roughly 1/10 or so if we view it. Just, well, yeah, I suppose as an undirected graph. Okay, a pretty obvious property is that on both the AS Internet and the World Wide Web, the older vertices tend to be more highly connected. Now, if you have a really popular, relatively new vertex, then it will also get a very large number of neighbors. Okay, probably the most interesting property is that these networks seem to have power law degree distributions. So what does that mean? Well, what it means is that if I look at a vertex and I ask how many neighbors it has, the probability that it has k neighbors falls off like k to some power. Okay, and the graphs that we as mathematicians have liked to deal with in the past fall off much more quickly than that. So to compare this, let's just look at, for example, a bell curve versus a power law curve. In a bell curve, most nodes have almost the same number of links, and there are essentially no highly connected nodes, because this is falling off very rapidly in K. In a power law distribution, you have a lot of nodes with a small number of links, but then you also have a reasonable number of them with a very large number of links. So these are the hubs that you see on both the World Wide Web and the AS Internet. Okay, so people actually started to see power law degree distributions, or started to talk about them back in the 1800s in the context of economic models. Then in the mid-1900s, Zipf noticed that there were power law degree distributions in some very reasonable sociological models, and people still talk about Zipf's law for power law degree distributions. The internet was measured in 1999 by 3 brothers, and they saw a power law degree distribution. And then shortly after that, a lot of people did measurements on the World Wide Web and also saw power law degree distributions. And on the World Wide Web, you had different powers for the in degree and the out degree. Okay, so if I looked at the probability that I had k people pointing in to my web page, that would fall off like k to the minus 2.1, and the probability that I pointed to k web pages would fall off like k to the minus 2.7, so faster. Okay, so it turns out that a lot of social networks look like these power law networks also. So if we look at acquaintance networks, these seem to have power law degree distributions. For example, the Club Nexus network at Stanford has, you can't see all the little lines here, but it seems to have a power law degree distribution. There are some people who are real hubs, okay, who have a lot of connections. Okay, so 6 degrees of separation. Where did this come from? Actually, it was a Hungarian author who in 1929 wrote a short story in which, I don't know how he came up with this in his short story, but he said that every pair of people on the planet is linked by no more than 5 intermediaries. In the history that I was reading about this on the web, and one of the problems with the web, of course, is that anybody can put anything up there, so it may not have been true, but people said, oh, people tried to prove this for years and years, and finally, in 1967, the psychologist Stanley Milgram empirically proved, which is an interesting term, the proposal by setting up an experiment. And what he did was he said, I'm going to pick a random person in the United States, and I'm going to give them a postcard. And they are to try to get that postcard to somebody else. I'll give them that person's name. I'll give them the rough area of the country in which that person lives, like let's say the Midwest, and I'll tell them what that person does. So, you know, I might have said, okay, try to send this postcard to Susan King, who is an elementary school teacher in the Midwest. Okay, and then I would have to try to figure out the person I want to give that postcard to, who I think is likely to know someone who knows someone who knows someone who knows someone who could get it to Susan King. Okay? And he found that it was about 6 degrees of separation. Okay. So, other social networks, I mean, we as academics have a different idea of social than other people do. So, this is our idea of social co-author networks. We have really exciting lives. Okay, so the InfoVis conference in 2004 had a contest to try to visualize co-author networks. And the winning entry had this very nice visualization. So the size of the nodes has to do with how many papers somebody has. And then you see all of these connections, and you see that there are some cliques in which everybody just writes papers with each other, you know, and then there's, you know, 1 or 2 people who might hook this person up with that person. Okay, so that's our idea of social. For other people, there are romantic relationship networks. For example, for high school students, non-mathematician high school students, there was a measurement in the American Journal of Sociology that showed a relationship network. So we had 63 monogamous pairs there. We had, 12 groups of, one guy who would go out with 2 different women, and 9 groups of 1 woman who would go out with 2 different guys. And then most people were connected to each other, okay? So then as people get older, you begin to worry about the spread of disease. And there was a paper in 2001 in which they looked at the log plot of the degree distribution of couples. So this is the number of partners, okay, and the red is women and the blue are guys, and this is self-reported. Okay, and people really do worry about this a lot. Okay, so models. What models would one use? Okay, so for simplicity, I'm going to look at models that explain the small diameter, the aging, and the power laws, but not the clustering. It is possible to come back and add some extra stuff to this so that one could explain the clustering. And so the models that I'm going to talk about are the preferential attachment growth models. And there are 2 classes. One is the undirected, and there's been a lot more work on that, and this is to describe the internet, co-author networks, things like that. Or there's one that we used for the World Wide Web, in which the edges actually have go from one site to a second site. Okay, so the undirected ones. Well, the non-rigorous study started about 80 years ago. Ewell was looking at models of this form. In the mid-1950s, Simon looked at models of this form, and then in 1999, Barabashi and his student Albert applied this to this was in response to the Faloutsos brothers who measured the power law on the World Wide Web, and Barabashi and his students said that they could apply this kind of stuff to the internet, and a lot of people call this the Barabashi-Albert model now. Okay, so what is this model? At each time step, a new vertex comes in, and it forms edges to two older vertices, and the probability that the new vertex attaches to the old vertex scales with the number of neighbors that the old vertex has. So this one has a lot of neighbors, so it's more likely that the new guy will form an edge to there. Okay, so if one doesn't worry about a lot of problems if you non-rigorously do this, you can do a back-of-the-envelope calculation, and you find that the probability that a vertex has k neighbors scales like k to the minus 3 in this model. Okay, so then, not long after this, the rigorous work came along. So if n is the total number of vertices in the graph, and m, just on the previous slide, is the number of vertices that each new vertex will attach to, then, and Bela, I'm not sure of the dates here, and I didn't know how to put accents. But, okay, we have the world's experts in the audience here. So they found that indeed this did have a small diameter. That had to do with the length, to get from one point to another point, the maximum of that. So if m was equal to 1, they found that it scaled like log n, and if m was greater than or equal to 2, a much harder proof showed that it scaled like log n over log n. And with some other co-authors, they showed that what was done in that back-of-the-envelope calculation, if you do it right and you add a uniform piece so that the model actually can start to grow, you do indeed get that the probability that a vertex has k neighbors goes like k to the minus 3. So these really are power law graphs. Okay, there's a directed one, and again, it's the same experts, plus a couple of other collaborators. So at each time step, one of 3 things happens with probabilities alpha or beta or gamma that add up to 1. With probability alpha, what happens is that you get a new vertex, and it sends an edge into an old vertex proportional to the in degree of the old vertex. So this is as if I make a web page and I link to Bela's web page. Okay, with probability beta, a new vertex comes out of an old vertex. So this is as if Bela posts a paper on his web page, okay? And it is proportional to the out degree. So people who post papers tend to post more papers. Okay, and the third thing that can happen is with probability gamma, an old vertex sends an edge. So there's an edge from one old vertex to a second old vertex, proportional to the out degree of the first vertex and the in degree of the second vertex. So this is just, if I have a web page and Peter has a web page, and our web pages have both been sitting there for a while, I might send a link to his web page. Okay, and if you go through this model, you find that you can get a power law for the in degree that is different from the power law for the out degree, and you can get the 2.1 and the 2.7 by properly choosing the alpha, beta, and gamma. Okay, so I've told you about power law networks for the internet, the World Wide Web, and for social networks. And now we're going to focus on models for the spread of viruses and worms. Okay, so I'll tell you what viruses and worms are. I'll tell you some of the observed properties, and then I will give you models for the spread of disease, for the spread of these viruses and worms, the so-called SIS model and SIR model. Okay, so viruses are programs that attach themselves to some host program, and you don't get infected by the virus unless you run that host program. So that's why they say, you know, be careful if you open a piece of email and it has an executable, you know, and it says basically click on this, you should be careful and not click on it because it might be a virus. Okay, worms are even worse. They break into your computer using some vulnerability that is left by the company, that's unintentionally left by the company that has made the operating system. Okay, and it doesn't require a user action to spread. So what happens is, you know, you turn on your computer in the morning, and if there is some worm going around and someone has tried to hit your computer with that worm and you have the vulnerability, boom, you just get it. Which is why when worms go around, you can see them spread around the world, you know, 9 a.m. in the US, or from 8 to 9 a.m., you just see this huge surge, and then, you know, you see it go from one country to another country. Okay, so I'll tell you what happened with Code Red, which was one of the very bad worms that went around. So about 10 a.m. Greenwich time on July 19th, 2001, the Code Red worm started infecting unpatched versions of a Microsoft web server. And what the worm did was that it randomly generated IP addresses. Okay, so most of them that it randomly generated didn't even correspond to any existing computers. Okay, but among them were some existing computers, and if those were not properly patched, then it would infect the ones that were not patched. Okay, and the worm infected about 360,000 hosts in 13 hours, and most of that happened over a period of about 5.5 hours, and the measurements show clear exponential growth over that 5.5 hour period. And then, starting at 4:30 in the afternoon, you saw the infection rate fall. So you still had a large number of hosts that were infected, but the infection rate fell. And this was due to the fact that some of the systems were patched, they were rebooted, and sometimes they would just pull them off the network. Okay, so if they pulled them off the network, then it was as if that node just disappeared from the network, so it couldn't infect anything else. Okay, now, so far, I was getting sort of tired and pulling funny things off the web. Anyway, so far, internet viruses and worms have been non-mutating. Actually, there has been one mutating one that's come around. But the next big threat, and the thing that most of the security people are really worried about, are mutating viruses and worms. So, for example, I could have a worm that knows of 100 different vulnerabilities, okay? And that worm starts spreading using one vulnerability. And it infects a large number of machines, like maybe 360,000 machines. And then at some random time, or at some fixed time, or at, after some fixed time lag, or maybe just in response to some command from a central authority, it says, okay, start using the second vulnerability on your list, okay? So people are busy patching for the first vulnerability, but now the probing, it's looking for the second vulnerability, and now instead of starting from one site, it's starting from 360,000 sites, and it does that, and then it keeps growing and growing. Okay, so obviously you can't effectively patch against a mutating virus or worm on the internet because you're always patching against the last thing. And this actually happens in human populations. The HIV virus, the reason that it is so problematic is because it is very rapidly mutating, and that's why there is no AIDS vaccine, because Whenever they try to come up with a vaccine, it's a vaccine for the last version of the disease. But you know, when it goes from one host to the next, it becomes a different disease. Okay, so what are models that people use for the spread of viruses and worms? Well, for mutating viruses and worms, you would have a two-state model. So each site, each vertex is in one of two states. It is either a susceptible vertex, so that means that it has the vulnerability that the worm is looking for, and so it can be infected. It's not infected yet, but it can be infected. And then there are the infected sites. It was infected and it's now infecting other hosts. And even if you were to cure it, to patch it, okay, then the worm would mutate and then it could get reinfected. Okay? The second model that people look at a lot is for non-mutating worms. It's called the SIR model. So each site is in one of three states. It is either a susceptible site or an infected site, or it is a removed site. So here, once you patch it, then it becomes an immune site, so the virus or the worm can't infect it anymore, or you might just, pull it off the network, then nothing can infect it anymore. So there are three classes of sites. So this one is a much harder model from a mathematical point of view because it has three states. This one is easy. It's still relatively hard, but it's easier from a mathematical point of view. But it's the harder one if you are a computer security person or if you're a doctor trying to come up with a vaccine. But since it's the easier mathematical one, that's the one that we're going to look at. Okay. So for SIS models, there are two versions. There's a continuous version, which is a differential equation, and this isn't that hard to deal with. The harder case is a discrete version, and it's also known as the contact process. And so the definition of that model is that you have two kinds of sites. So you have a site which has the worm, and that will actually recover at some rate rho. So it goes from an infected state to a healthy state. A healthy state is still a susceptible state because the virus is going to mutate. And it goes from a healthy state to an infected state at a rate beta times the number of infected neighbors. So if you have a lot of infected neighbors, you are more likely to get the worm. Okay, and the relevant parameter lambda is the transmission rate over the cure rate. Okay, and this is widely studied in probability theory and physics, and also for the mutating case, it's actually studied for the spread of diseases. And it was first applied to viruses and worms on a computer network in 1993. Okay, so we're going to look at the discrete version, not the continuous version. And so what has been known about that? What's been known for some time? Well, if I look at the model on a bounded degree infinite graph, then it has a phase transition. For example, on the cubic lattice. So what happens is that if lambda, the parameter which was the transmission rate over the cure rate, is less than some critical value, which is called the epidemic threshold, then if I start the infection out from a finite set, it will die with probability 1. There's just not enough for it to take off. The system will cure itself. Okay? However, if lambda is greater than lambda c, then we actually then the infection actually survives with positive probability. Okay? So that is what we mean by an epidemic, if it survives with positive probability. Okay, now if I look at the SIS model on a finite bounded degree graph, then it has to die out eventually, right? Because it could be this, you know, at some time, some small segment of time, essentially everything cures itself. But the question is, how long will it take? And so if lambda is less than lambda c, it turns out that if on the full lattice, it would have died out with probability 1, then on the finite lattice, it will survive a polynomial amount of time. And if the infection would have survived with positive probability on the full lattice, then on a finite subset, it will survive much longer. It'll survive super polynomial, usually exponential. Okay, so when we prove things, we'll prove super polynomial amount of time, and then we'll say that we're in this region. And the question is, what happens with a preferential attachment graph rather than a bounded degree graph? Okay, so we are finally on the third part of the talk. So what we're going to do is that we're going to put together the power law networks and this SIS model, and we're going to ask what happens when we put an SIS model on a power law network. Okay, and so this corresponds to having a mutating virus or worm on a computer network or a social network. Okay, and so the first thing we will do is we will talk about the spread on these preferential attachment graphs. And the second thing we'll do is we will ask, how can we contain these epidemics? Is there something that we can do to contain them, and not only on preferential attachment graphs, but on general graphs? Okay, so the questions we're asking, the question we're asking here is, what is the epidemic threshold of power law graphs? Okay, and we saw that for ZD, or for a finite piece of ZD, there was some lambda c. So we're asking, what is lambda c for a preferential attachment graph? And the second thing that we want to know is that if we had a certain amount of antidote, so if instead of having something like, you know, row units of cure per site, we could take that and we could distribute it non-uniformly. So I could give more of the cure to some sites than to some other sites. Would there be a way of trying to control the epidemic on a general graph? Okay, so the first question was, what is the threshold of the SIS model on a preferential attachment graph? And it turns out that on preferential attachment graphs, the epidemic threshold is 0, asymptotically almost surely. So what that means is that if there is any positive rate of transmission to the neighbors, okay, so if that beta is positive, no matter how small it is, then with positive probability you will have an epidemic. Okay, so on these power law graphs, it's much worse than on ZD. These things really spread. And the physics argument for this was given in 2001, and we gave a proof of this in 2004, and we went a little further than the physics argument. We also showed what the survival probability of the virus was as a function of lambda. Lambda was the transmission rate over the cure rate. Okay, so we look at the SIS model on a preferential attachment graph of size n. Okay, so once again, the SIS model says that every site is in one of two states. It is either susceptible, it doesn't have the disease, but it can be infected by it. And then at rate rho, the ones that have the virus will cure themselves, like getting patched or something. And at rate beta times the number of infected neighbors, you will get the disease, okay? And so if we start the infection out from a uniformly random vertex x, so I'm just going to pick some random vertex, then with probability 1 minus order lambda squared, that site is such that the infection survives a super polynomial length of time with a probability of order lambda to some constant. We actually have upper and lower bounds with different constants. Lambda to the log 1 over lambda over log 1 over lambda. So let's just think about what that is. I want to think of lambda, the transmission rate, as pretty small, right? And then 1 over lambda is big. So log 1 over lambda is big. And just forget about log 1 over lambda because it's smaller than log 1 over lambda. So I have a small number to a big power. So this is a very small number. Nevertheless, it is a positive number. Okay? For any lambda, that's a positive number. And that means that lambda c is equal to 0, because for any positive rate of transmission, you are going to have a positive probability that the virus survives a super polynomial length of time, which means there is a positive probability of that virus taking off. Okay? So, notice that I said with probability 1 minus order lambda squared, the site x that I chose is such that blah, blah, blah. Okay, but what that means is that of the n vertices, I was leaving out of order lambda squared n of them, so some small number of them. What do these vertices do to the average survival probability? And they actually affect it dramatically. So the second theorem, we look at the same thing, and now I say that the infection starts out from a uniformly random vertex x, and I don't say, you know, with probability blah, 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 x is such that. It starts out from a uniformly random vertex x, and it survives a super polynomial length of time with probability of order lambda to some different constant. Okay, now notice this is much, much bigger than that, because this is just lambda to a constant. This is lambda to some really large power. Okay, so what's happening is that the average survival probability is much larger than the typical survival probability. Okay? The survival probability if the infection starts from a typical vertex is this order, whereas the average survival probability is much larger. And why is that? This is due to the presence of some high degree hubs. So if I start out a web virus on, you know, the CNN website, okay, well then we're going to have some trouble. Or the AOL website, then we're going to have some trouble. So if you manage to start it off at some highly connected site, then you're in a lot more trouble. Okay? So, now the last part of the talk I think is the most interesting. So what do we do to try to control the spread of these viruses on a general graph? So if I had a fixed amount of antidote, what is the best way to try to distribute this antidote to contain the epidemic? And what do I mean by to contain the epidemic? Well, okay, we noticed that with bounded degree graphs, there was a phase in which the virus died out with probability 1, and then there was a phase in which it became epidemic. So what I would like to do is do something to redistribute the cure so that we actually get a phase in which we don't have an epidemic, okay? Lambda c was equal to 0 if we just said everybody gets the same amount of cure. So we want to try to redistribute it. So this is what we worked on last year. So for the rest of the talk, the first thing I'm going to do is I'm going to just go over for you once more the definition of the standard SIS model. I'm then going to go back to that theorem 1, and I'm going to look at how lambda c goes to 0. I told you that lambda c was 0, but I didn't tell you how it went to 0 as a function of n. And I'm actually now, lambda was beta over rho, the transmission rate over the cure rate, and now I'm going to look separately at the transmission rate and the cure rate. And the reason that we're going to do that is because we're going to let the cure rate vary from one vertex to the next, but we're going to assume that the total amount of antidote, the cure rate times the number of sites, is fixed. And we're going to ask, how do we distribute this antidote most effectively? Okay, so the SIS model, I showed you this before, but just so that just to keep it in your mind, if a vertex has the virus, then it cures itself at rate rho. If it doesn't have the virus, then it will get it at a rate beta times the number of neighbors that have the virus. And we said that the relevant parameter was beta over rho. So now let's go back to theorem 1, and let's look at it in two cases. Okay, so for a star, so this is a much simpler graph than a preferential attachment graph. A star is just one vertex with a lot of other vertices around it. Okay, and it turns out that if I look at how lambda c goes to 0, so lambda c is beta c over rho, it goes to 0 like 1 over square root of n. Okay, so what does that mean? Well, if I wanted to make this not go to 0, I would have to have rho go like n to the plus 1/2, okay? That would mean that the amount of antidote that I would need is the number of vertices times the amount of antidote per vertex, which if I didn't want beta c to go to 0 would have to be n to the plus 1/2. So this would be like n to the 3/2, so super linear in n. So let's say that we had a population of 1 million people, okay? Then each person would have to get something like 1,000 doses, and if we had them like this, okay? And I said I want to give the same amount of cure to everybody, the same amount of Tamiflu to every person, then I would have to give like 1,000 units of antidote to each person, okay? And for preferential attachment graphs, I'm not going to tell you how beta c goes to 0, but the fact that it does go to 0 means that it must be the case that I have something that goes to 0 with n here. And so to compensate for that, rho would have to go to infinity with n. So the amount of antidote would be something that goes to infinity with n times n, superlinear in n. Okay, so now what I want to do is I want to vary the recovery rate. So I want to assume that there is a fixed amount of antidote, okay? So, you know, we have a fixed amount of Tamiflu, bird flu is going around, we have a fixed amount of antidote, but I don't want to say every individual gets the same amount of Tamiflu. I want to distribute it non-uniformly, okay? So what is the best policy? And is there a way to control the infection, i.e. to get lambda c bigger than 0 on a star or on a preferential attachment graph with having A scale linearly with n, so not having the cure rate scale with n. Okay, so method 1, which is a method that's used a lot, is called contact tracing. So, you know, if some kid gets the measles, okay, then, you know, every kid in his class then has contact with somebody who has the measles, and maybe all those kids will get a shot against the measles. Okay, so contact tracing, you look out from one person to the people who have contact with them, and so on. Okay, so contact tracing is used a lot, and what they do is they want to treat the contacts of the infected individuals. So they want to augment the cure rate of the neighbors of the infected nodes. So the amount of cure, the amount of Tamiflu I'm going to give you is not going to have to do with your degree, it's going to have to do with your infected degree. So if you have a lot of people you've been in contact with who have the bird flu, then I should be giving you a lot of Tamiflu. Okay, this is if the bird flu is very rapidly mutating. Okay, so what our theorem says is let's just look at a star and let's let the amount of cure that I give you scale with the number of infected neighbors you have. Then the critical infection rate it still goes to 0, unfortunately, and it goes like rho n to the minus 1/3. So note that this is an improvement of the case in which we were giving the same amount to everybody, in which case this went like n to the minus 1/2, but it still gives beta c goes to 0. So to have this thing not go to 0, I'd have to have rho grow like n to the 1/3. So in a population of 1 million, I'd still have to give about 100 doses per person, times the appropriate constants. Okay? So, and it's kind of disturbing that this happens because this is what epidemiologists do. They do contact tracing. Okay? And so let's say that we do something that seems much stupider, okay? I'm not going to look at what has happened already. I am just going to give cure proportional to the number of neighbors that you have. Not the number of infected neighbors, just the number of neighbors that you have. Okay? And what we prove here is that if we let that be the case, if we let the amount of cure be the number of neighbors that you have, then if beta is less than 1, the expected survival time is very short. In other words, we've got a phase in which the virus doesn't spread. So the corollary is that for a bounded average degree graph, the total amount of antidote that's needed is linear in n. Okay, so this actually works well, and this is on a general bounded degree graph. So curing proportional to degree is enough to control epidemics on general graphs with bounded average degree, and this includes preferential attachment graphs. Okay, and the big difference here is that if you have let the virus take off with contact tracing, and it's in a lot of the population, then even if you're giving Tamiflu to the people who have a lot of infected neighbors, okay, you're not doing it in time to catch the disease. Whereas if, so that's if it's already taken off. If you do it very, very early in the game, then you may be okay, but typically what has happened is if it's already taken off, you're not going to be able to control it. But here, if you just say, I'm going to take the people who have a lot of contacts, and we do this too. We say we're going to take hospital workers, okay, and we're going to inoculate them, okay. So if you take the people who are going to have a lot of contacts, then you'll do better. Okay, and the final question we ask is that can we do even better? Can we push beta C up to infinity as n goes to infinity? So right now what we've been able to do is we've been able to give ourselves a phase in which the virus doesn't spread. Can we get the whole phase diagram to have the virus not spreading? Okay, and the answer to this is no for expanders. And what an expander is, basically, I mean, here's the real definition of it, but it's a graph with a lot of boundary relative to volume. Okay, a lot of boundary. And so what you should think of if you're thinking about epidemiology is if you have an expander, it's very hard to do quarantines. Because what you want to do is you want to isolate populations. Okay, but if you have a lot of, boundary, then how do you isolate? You have to cut too many links. So you can just think of an expander as something that you can't quarantine very well. And then I've got a technical condition here which basically says that the amount of cure that you have can't be more than the amount of edges you would have in any subset. So what our theorem says is that if we have a sequence of expanders, then if beta is bigger than the average degree over something that has to do with the expansion rate, the survival time is really long, okay? It's super exponential, okay? So, so in other words, if beta or if lambda is big enough, then it's going to take off, okay? And so what this tells us is that nothing can do more than a constant factor better than inoculating according to degree. Okay? Now you may care about that constant factor, But the point is, you're not going to be able to do anything that's more than a constant factor better. Okay, so the summary is that on preferential attachment graphs, mutating viruses and worms which have any positive rate of transmission to their neighbors and a constant recovery rate become epidemic with positive probability. So viruses really take off on preferential attachment graphs. Okay, contact tracing, which is a method that is usually used by epidemiologists, does not control the epidemic in the sense that on a star, it would still give beta C equal to 0. On general graphs, curing proportional to degree does control the epidemic in the sense that it at least gives us a phase in which the epidemic doesn't take off. So that's the way we should do it. And for expanders, which is what a lot of our society looks like, with bounded average degree, no other inoculation scheme is going to do more than a constant factor better than this scheme here. So that's it. Yeah, definitely.
Chayes, very please answer some questions from you. Any questions?
There's a question up there.
Yeah. Is there any general deep result that says why the scaling factor has to be between 2 to 3? We observe that the power law is always between 2 to 3. So.
Well, actually, in many, many cases, it turns out, like in most biological cases, and as they go back and they look at the data more closely, they're finding that in most cases, it is actually from 1 to 2 and not from 2 to 3. So the web still looks like it's from 2 to 3, but in most other cases, it seems to be between 1 and 2. The recent measurements on the internet are right around 2. Co-author networks, biological networks. A lot of people are looking at biological networks now that have to do with various enzymes, you know, pathways of enzymes, that kind of thing. They're actually finding power laws that go from 1 to 2. So it seems actually that is even more general than the 2 to 3. And it's much harder to get that from a Barr-Bashi-Albert type model, actually. Mm-hmm.
I was wondering for the study, your work on the epidemics on the PA graphs or general graphs in general, is there an implicit or an explicit assumption that the underlying graph has already reached a steady state, or it is static, or it is...
No, this is on the growing graph. We've said for n large enough, okay, but we are on the growing graph.
So the graph is still in the process of growing?
It's in the process of growing because, you know, and maybe you'll hear us, well, me and Christian and some other people talk more about this in the workshop next week if you come to that. We really have to be looking at the properties of sequences of growing graphs. What we've done in the past with graph theory is, you know, we've looked at fixed graphs. But if we want to describe these technological networks, these social networks, we really need a theory of asymptotically large growing graphs. Yeah?
All graphs where the nodes die, meaning connections lose out after a point in time. Talk about growing graphs. I presume that in epidemiology,
Right, well that's like the SIR model, okay? And if you look at our proof, which I didn't show you, of why the epidemic takes off for any positive lambda, it really depends on the fact that you are not removing lots, the dying or being cured and then being immune really takes you to the SIR model. And in the SIR model, you are going to see some of this, but it will level off eventually. Okay, so it'll have a very different behavior. But as I said, with mutating viruses and worms, you are going to get this kind of behavior. Okay, and also with things like the HIV virus. Okay, so there are cases in which you really do get this kind of behavior. But when things really either die or get cured, when a large percentage of things either die or get cured, then you will have different behavior. Mm-hmm.
As far as I see, most of the cure suggested here is to cure the nodes. Can you think something of cutting off the prominent edges in terms of
Cutting off?
the prominent edges or the links connecting to infected? Possible or
Well, if you're talking about cutting things, what you're trying to do is quarantine, really. I mean, standing in the wrong place. So you're trying to quarantine, and it's very hard to quarantine the hubs. I mean, sometimes a systems administrator tries to do this, right? You might pull your whole company off the web, or you might say, AOL is just going to pull itself off, to try to stop the spread of a worm. But that's a very hard decision to make. And companies will do that because in companies, they have the power to say, we're going to pull you off the web. But if you're an AOL subscriber, you might get furious if they just pull you off, okay? Or off the AS internet.
Any more questions? Well, I think we have a lot of things to think about. Not just for internet or the World Web, also for the avian flu. Anyway, let's please join me in thanking